Okay, so now we're going to talk about measurement of kinematics in 3 dimensions. On the top of the slide here, you'll see a tweet that I've taken a screenshot of. And this is from very well-known golfer Rory McIlroy when he visited our lab when I worked in Leeds Beckett University. Now, where 3-dimensional kinematics are different to 2-dimensional kinematics is how we are measuring the movement and in what planes of motion. You will all know that the body moves in 3 main planes of motion, and we've already spoken a little bit about sagittal and frontal plane when we talked about 2-dimensional kinematic analysis. The one plane that is impossible really to measure or very difficult to measure in 2-dimensional analysis is the transverse plane, where we have any type of rotation. And 2-dimensional analysis can only measure any one of these planes at any time. The advantage of 3-dimensional analysis is it can measure all 3 of these dimensions at one time. To use 3-dimensional video or kinematic analysis, it requires multiple cameras. At a minimum of 2 cameras is required. Usually we need more because the movement may be very complex and we may not capture all of it with just 2 cameras. The 2 cameras that we utilize need to be capturing or recording simultaneously. Therefore, we need to start both cameras at the exact same time. We typically use a trigger or an external input to allow us to do that. The other important thing that you should be familiar with is frame rate, and that also needs to be the same on all or both cameras that are being used. This is an example, a very basic schematic or line drawing example of what that might look like. And in this example there are 2 cameras being used, and they're actually placed directly perpendicular to each other. But by having both of these cameras looking at the participant from 2 different angles, it could allow us to measure movement in 3 dimensions. Now we also need to calibrate a 3-dimensional kinematic data collection system. And the calibration for 3 dimensions is a lot more complex, as you would imagine. We need at least 6 known points in order for us to complete the necessary equations to calibrate any capture volume, as we would call it in 3D space. These points cannot be in a straight line, or otherwise stated, they must not be non-coplanar. And they must be distributed across all 3 planes, so horizontally, vertically, and I suppose transversely, or in the case of a 3-dimensional volume, with depth, so front to back. The points, all 6 or more of them, must be visible on all cameras. And whatever we use for calibration must be rigid and stable and easily movable or portable. Again, once the cameras are calibrated, they cannot be moved. This is an example of what we could use for a calibration for a 3-dimensional volume. Each of these poles has 2 defined points that were used for calibration. We can see the black mark at the bottom of the pole and the black and white mark located midway up the pole. Each pole was placed at the corner of the volume we wanted to record data in. The poles were located 1 meter apart in depth, 5 meters apart in width, and the top marker was located 2 meters above the bottom marker. So marker 6 here is 2 meters above marker 2. Marker 2 is 1 meter in front of marker 1. Marker 3 is 5 meters horizontally away from marker 2. So that defines a 1 by 5 by 2 volume or space that we want to capture 3-dimensional data in. So in this case, if we had 2 cameras, they would both look at this volume from a different perspective and see those, in this case, 8 markers from a slightly different angle. The location and the coordinates of those 8 markers would be inputted into a specific calibration matrix to allow us to measure movement in 3 dimensions within that space. So, let's go back to thinking about our cyclist. Yes, what's most interesting to us for our cyclist is his movement in the sagittal plane, his flexion and his extension. But perhaps we're also interested in his frontal plane movement of his knee. So how does his knee come out towards the camera? And we want to measure that at the same time as his flexion and his extension. To give you a visual of what that might look like, this is a really nice YouTube video that I found to illustrate a 3D biomechanical analysis of a cyclist. We can see here, this is just typical video footage. What they're showing us is the participant against a contrast background with a range of retroreflective or reflective markers placed on different parts of the body. We can see them on the pelvis, further up the back. We can see them on the hips, the thigh, the shank, on the feet, and also on the pedal itself. Now we can see what that looks like when we actually convert it into 3-dimensional data. And what's very interesting, and what we were speaking about, is the side-to-side movement of the knees is very clear and very easily measured when we capture data like this in 3 dimensions. The real nifty thing about recording in 3 dimensions is we can rotate around the view like this. And we can look at the cyclist from any different perspective. We can look at him from the side, we can look at him from the front, from the back. If we wanted to, we could even turn him upside down, look at him from underneath or from an overhead view. It can be very valuable to look at the very finer specific details of a movement. And for this athlete, we can see he's not doing too badly. His left knee has a little bit more side-to-side movement than his right. Of course, we can still get the same standard sagittal plane data, but it's actually a little bit more valid when we incorporate it in this 3-dimensional view, because it encompasses any of that side-to-side movement and how it might adjust the sagittal plane angles. So, what would that look like if we were trying to graph it? And this is my best attempt at trying to do that for you. So if we were looking at that knee, that one point of very important interest, instead of just having 2 coordinates now, we have 3. We know how far horizontally, from left to right, the knee is located in space. We know how high, from top to bottom, it is located in space. But within the volume that we've defined, we also know the depth, so how far away from us, from the cameras, from within this volume that knee is located. So instead of looking at the movement like it would display on a piece of paper or on a picture, we are now looking at it how it would happen within a cube. Looking at the movement from front to back, side to side, up and down, in all 3 dimensions. So the important thing to take away from this slide is that in 3 dimensions, our coordinate now has 3 points: horizontal, vertical, and depth, essentially X, Y, and Z. There's one limitation or thing to consider when we are trying to measure that Z, and especially transverse rotations. The image we see on the slide right now is a representation of a segment. Think of anything. Think of a baseball bat, for instance. Q would be the top of the baseball bat. The point P would be present at the bottom of the baseball bat. If we were to turn the baseball bat in the sagittal or the frontal plane, it would be very observable to the naked eye. It would be easily for us to see that occurring. If we were to track that and we had a marker placed on the top and the bottom of the baseball bat Again, it would be easy to measure and identify that. However, if we were to rotate that baseball and then we only had that baseball bat and we only had 2 markers placed on the top and the bottom, there wouldn't be enough distinguishable movement in those 2 markers to distinguish or identify that vertical plane or transverse plane rotation. Therefore, when we want to define rotation of a segment, we need to place 2 or more markers on it, like is nicely visually represented here in this image. That's all for section 2. You can now progress onto your last, final concluding section, where we'll talk a little bit about some analysis and research examples.